The title of this presentation is WEB.BM, a decision support system for integrating hydrological forecasts into reservoir and basin planning and operation. My name is Dr. Neša Ilić. The company's website is www.optimal-solutions-ltd.com, and the WEB.BM model can be accessed at www.riverbasinmanagement.com. In the presentation outline, we first have a quick introduction to the WEB.BM, a few notes on the classical rule curve concept, the replacement of the rule curve concept with a multi-period or MTO optimization for drought management with seasonal forecasts, MTO for floods, where the concept of the model predictive control optimization will be introduced based on the assumed short-term forecasts. The WEB.BM stands for Web Basin Management. It is a web application that combines the COIN-OR linear programming public domain solver, Microsoft SQL Server database, and the Google Maps interface. The model can solve reservoir optimization problems for single or multiple time steps and for any time step length, such that it can be used both as a planning and an operational model. It includes all constraints that are relevant to river basin models, including nonlinear hydrological routing. Linear programming formulation of river basin allocation is given on a simple example with 2 reservoirs, 2 irrigation blocks, and 1 diversion canal. The idea is to find water allocation in the basin which maximizes the objective function, given as a sum product of all allocated flows and the pricing vector Pi. Now, the pricing vector Pi is essentially the value of water given to various components. For example, you can see that in the reservoir we have 3 storage zones. It's a very high value for keeping storage up to the dead storage level, and then a very low value of only 5 for conservation storage, which means the conservation storage will be giving water to other components. There's also a negative value which expresses the undesirability of being above the full reservoir level. This is a flood storage zone, and it is not desirable to stay in that zone, especially not during normal conditions. The diversion canal has a higher value of 1500. This implies that diversion will be pulling water from storage. Downstream we can see this river channel having 2 zones. There is 0 payout factor for having flow below 3000 cubic meters per second, while there is a very high negative value for having flows above 3000 cubic meters per second, which means that the flood threshold is 3000 cubic meters per second. Before this threshold is violated, water will be first placed in the flood storage zone in the reservoir. Now, this kind of formulation is used in all other known linear programming based models, such as the Riverware, Oasis, ModSim, or the WEB model, which are frequently used in many studies. They all use the same pricing vector concept. This is what the interface of the model looks like. You can see that there are several options here. For the time being, the most important options to note are the instructional videos and the user manual option, which are available to users as soon as they log in. By the way, to log in, all you require is to sign up with any email ID. A quick review of the rule curve concept. Reservoir operators are typically assisted by defining the upper rule curve based on the flood studies and defining the lower rule curve based on the drought studies. Both curves are usually fixed for all years. Currently, both curves are created using trial and error simulation. The alternative to rule curves is a combination of runoff forecasts and multiple time step or MTO optimization models. Now, these models require seasonal or short-term forecasts. This idea is not new. You will be able to find this paper in the American Society of Civil Engineers library. The paper is titled Death to Rule Curves, and it was presented at a conference in 1999. The name of the conference was Preparing for the 21st Century. What is interesting is that the combination of the runoff forecast models and multiple time step optimization, also known as multi-period optimization, provides the users with the tool that actually generates perfect reservoir operation, assuming the forecast is perfect. And as we improve the forecasts with the use of remote sensing and artificial intelligence, we are moving closer and closer to automated operation of dams, much like the self-driving vehicles in transportation industry are changing that industry. So the multi-period or multiple time step optimization is demonstrated on a very simple example here. We're looking at one reservoir which has a known inflow for the first time step, and it has a known starting storage. We have 2 river reaches and 1 water user. The dashed line represents the storage value at the end of this time step. Now, if we assume that this dashed line is automatically the starting storage for the next time step, in other words, we copied and pasted this system to the right, and we are going to be able to solve 2 time steps at once, or possibly even 3 time steps at once. Note that these inflows Q2 and Q3 are inflows in possibly day 2 or day 3, so they have to be forecast, they are not known. It could also be week 2 or week 3, depending on what time step is used. If we are solving the model this way, then the model will produce the best trajectory of reservoir levels. If we add one more constraint, which ensures that the ratio between supplied and demanded amount in each time step is the same, then we are going to see equal deficits spread over the entire irrigation season. So if the yellow line here is the crop demand curve and we don't have enough water to meet 100% demand in dry years, then the model will determine where the blue line, which is the actual allocation, is going to be. In other words, the model will simultaneously find the best trajectory of storage levels and the best level of demand hedging simultaneously as part of a single solution. What are the benefits of this? Well, if we have seasonal forecasts, we don't need to put the rule curve into the model. The model will actually create the optimal reservoir trajectory, which is de facto the optimal rule curve. In the same time, the model will concurrently optimize demand hedging together with the storage management. This is done using linear programming, which guarantees finding a global optimum, and it does it very quickly. Compared to any other solvers, linear programming is the fastest solution technique we have. This is one way to improve the current level of operation without having perfect forecasts. The other way is if you look at, for example, a very simplistic schematic of the Nile River Basin, we see a potential conflict between the upstream irrigation and downstream hydropower generation. The more we increase irrigation, the more downstream hydropower producers will suffer, and vice versa. So there have been many papers in the literature published using various heuristic solvers that provide a multitude of solutions within the so-called multi-objective programming framework. They typically involve a lot of computations and analysis of many solutions. If we were to use the linear programming based trade-off analysis, all we would need to do is create 5 or 6 scenarios where we would consider the irrigation demand to be at either 100%, 90%, 80, 70, or 60, for example, as different demand targets. And then we would set up the multiple time step optimization scenario and find the best possible solution for each of those scenarios. Once we have that, it will be easy to create these 5 points on a graph where we have total irrigation supply on the x-axis and total generated power on the y-axis, and this will be our Pareto optimal front. The advantages are that each and every one of those solutions is guaranteed to be globally optimum, and the other advantage is we can get the solution for each of those scenarios within 1 minute of computational time. Some recent papers that I reviewed mentioned 700 hours of computational time for various scenarios and hundreds of solutions that had to be generated to find something similar. The most interesting and probably the most attractive feature of this modeling solution technology is the so-called model predictive control solution, where we're looking at shorter time steps. This could be used either for managing floods or managing day-to-day operation. We see an example of a simultaneous solution for 3 days, where the release from the reservoir in the first day will not reach a downstream user in the first day, won't even reach in the second day. It'll take 3 days to reach the downstream user, and you can see how the release from the first day has moved into the second river reach and then into the third river reach in the second and third day. Of course, as it moves, it also attenuates, so we have to include the attenuation in the solution process. So when we are solving for the first day, we are assuming the forecast for the next 2 days, and this is schematically shown in the figure in the upper right hand corner, where the black color indicates that the solution will be accepted only for the first day, but the forecasts of inflows for the second and the third day will be incorporated in the solution. As the day progresses from one to the other, we keep updating the starting storage levels, and we keep using the updates for the forecast as well. It's important to note that these solution procedures cannot be incorporated in simulation models. You have to have an optimization model, because simulation models only solve one time step at a time. The application to the Damodar River Basin in West Bengal in India is shown here. We have 5 reservoirs. These 2 reservoirs, Maitan and Panchet, have a very large flood control storage of almost 1 billion cubic meters combined, not individually. The idea was to figure out how to protect the downstream river reach, which goes through a heavily populated area. We had data from 1961 to 2017, daily data. In this period, there were 11 catastrophic floods. What we managed to show is that only with 2 days of runoff forecast, we'll be able to tame 9 out of those 11 floods completely, and the other 2 would only cause a minor incursion to around 3,500 cubic meters per second or less. Here is the most downstream channel which is being protected. With only 1 day time lead or 1 day forecast, we still have a large flood of 5,500. However, as we increase the forecast, the savings increase dramatically, and with the 3 day forecast, we are only about 200 cubic meters per second above the threshold. With 4 day forecast, there is no flood damage at all. Here is a plot of the reservoir levels that shows that as we increase the time lead, the pre-flood drawdown on both reservoirs starts earlier and goes deeper, and the deepest is the green line, which includes the 4 days time lead. Finally, there is another similar study that was done in a different basin that has 4 reservoirs. There is a lot of routing, and there is a tributary inflow here and tributary inflow downstream at this. These are 3 hourly time steps. You can see the diagram on the right hand side, where the black solid line shows the natural flood as it would occur if there were no reservoirs at all. Then we see the reduction of the natural hydrograph with only 1 day forecast, and then 3 day forecasts, and again 4 day forecasts. Thank you very much for your attention.